All right, I think I got this figured out. Hello, welcome. We're going to go ahead and we're going to pick back up right where we left off yesterday. We were getting into 12.5, which was arc length and curvature. So let's go ahead, let's jot down where we left off yesterday. So the idea was we started off with a curve given by some vector valued function that we're going to call r of t. And we're going to let this be just a plane curve for now, but the same thought process that we're going to go through could be used if we were talking about a curve in space. So let's actually go ahead and let's write down this curve as some x of t, comma, y of t. And we can go ahead, we can just kind of doodle whatever curve we would like to sketch. And that's going to be my curve r of t. Now, what we were in the middle of trying to find yesterday is we were in the middle of trying to find the length of this curve, or the arc length, between 2 points on the curve. So at some time t equals a, and maybe at some other point t equals b. So what we're trying to come up with is we're trying to come up with a way to find the distance along the curve, or the arc length, between t equals a and t equals b. And what we said we could do is we could pick a small point somewhere on our curve. So I'm going to imagine drawing an infinitesimally small point on my curve, somewhere right about there, and I'm going to imagine that I zoom in on it. So if I zoom into that circle, what I'll see is I'll see something that's going to look like a straight line segment. Right, so zoom in far enough on your curve will look like a straight line segment as long as it's relatively smooth. Right? So we're going to call this little segment some ds, a small sliver of arc length. So what our arc length is going to be, we'll call arc length capital S, is going to be the sum of all of these little pieces of arc length. But it's a sum of infinitely many infinitesimally small pieces of arc length, and to denote that, we can write it as the integral of ds. And where are we getting all of these pieces of arc length from? Well, we're starting with the piece of arc length over at t equals a, and we're going to end when we get to t equals b. So technically, we have an integral set up to find arc length from t equals a to t equals b, but there's really nothing for us to evaluate here. S was something that we introduced, ds was something that we introduced. Really, we need to tie this back to our curve somehow. So the way that we do that is we go back to our little sliver of arc length and we ask, well, where did this piece of arc length come from? This little change in S came from a change in X and a change in Y. So instead of thinking about that little piece of arc length as some ds, we can apply Pythagorean's theorem, and we could think about ds as being the square root of dx squared plus dy squared. So now we can come up to our integral, and we could replace that ds with a square root of dx squared plus a dy squared. And our limits of integration are still in terms of t. We're still going from t equals a to t equals b. And because our integrand is not in terms of t and our differential is not in terms of t, I'm going to explicitly write the integral from t equals a up to t equals b. So now we're at this point in the problem where we've got ourselves an integral where we don't have a differential. So we don't have a something times dx or something times dy or something times dt. And we need to figure out how to rewrite this so that we do have something which we can, in fact, integrate. So here's the trick. We're going to do a little trick here. We're going to go through and we're going to multiply both dx squared and dy squared by dt squared and divide both by dt squared. So what that's going to look like is I'm going to imagine multiplying everything under the radical by a dt squared, but also dividing everything by a dt squared. So that'll leave me with something that looks like this. As soon as I lift my pencil up, this is going to go away. So if you'd like to jot this down, now would be a good time to pause the video. Otherwise, we're going to jump into the next step. So the next thing that we'll see will happen is that this square root and the squared will cancel one another. And what we'll be left with is something that looks like the integral of the square root of dx over dt quantity squared plus dy over dt quantity squared. And we took the square root of dt squared, so we do have a dt all the way to the right of our integrand. So what's interesting now is now I have a differential of dt. So when I write my limits of integration, I no longer need to explicitly state that I'm going from t equals a to t equals b. I can just say this is the integral from a to b. But now we just need to interpret dx dt and dy dt. Well, dx dt is just the derivative of the x components of our curve. Dy dt is the derivative of the y components of our curve. We got those all the way back in the definition of our curve. So we could actually go through, take this one step further, and write this as the integral from a to b of the square root of x prime of t quantity squared plus y prime of t quantity squared dt. Now, there's one more place that I want to take this. So the last place that we're going to take this is we're going to look at our integrand. I feel like this resembles the magnitude of a vector. We have a square root of something squared plus something else squared. So this kind of feels like it would be the magnitude of r, but we have an x prime and a y prime. So this isn't the magnitude of r. Instead, it's the magnitude of r prime. So we could go through here, and we could finally write this as the integral from a to b of the magnitude of r prime of t dt. Now, the cool thing is that we went through this in the plane. But if we imagined working through the same idea in space, the big change would be that here we'd also have some sort of change in z values, depending on how we wanted to orient our three-dimensional space, which would mean that we'd have a plus dz squared here, which would mean that we'd have a plus dz squared here, which would mean that we'd have a plus dz dt quantity squared here, which would mean that we'd have a z prime here, and we'd still be left with the integral from a to b of the magnitude of r prime of t dt. So regardless of if we're in the plane or if we're in space, we could say that the arc length of a curve represented by a vector valued function is the integral from a to b of the magnitude of r prime of t dt. Okay, so this next little theorem is just exactly what I had just said written out. So the arc length is that integral from a to b of r prime of t dt. In the middle, I have this little statement saying that it's equal to the integral of this ds, and then there's a c written as what looks like the lower limit of integration. This is just a notational convenience that we're going to use quite often throughout the course. So what this right here is saying is it's saying I have a curve c that looks something like this. And what I want to do is I want to go through and I want to find all of these little pieces of arc length. So I've got all these infinitely many infinitesimally small slivers of arc length. And to add all of these together, well, I want to go along the entire curve and I want to add all these little slivers of arc length together. I know you can't see my hand. All right, let's go and let's try out example 56. It's going to be as straightforward as it sounds. It's a setup, but do not evaluate a definite integral to find the arc length of the curve given by r of t equals sine of t, cosine of t, t squared on the interval from 0 to pi. So we have this nice formula for arc length. It's going to be the integral of the magnitude of r prime of t dt on the interval. Well, the interval that's spelled out in the problem is from 0 to pi. So our lower limit will be 0, our upper limit will be pi. And now it's just a matter of going through, finding our magnitude. So the magnitude of r prime will be the square root of, well, r prime's x component is going to be cosine of t. So we'll have a cosine squared of t. R prime's y component will be a negative sine of t. So we'll have a plus negative sine of t squared, which I can just write as plus sine of t squared. And then finally, the derivative of the z component is going to be 2t, and 2t squared is going to be a 4t squared. And this is being integrated with respect to t. At this point, we could say that we're done, Or we could recognize that we have a cosine squared plus a sine squared. That's an obvious Pythagorean identity. Let's go ahead and let's invoke the Pythagorean identity just to rewrite it as the integral from 0 to pi of the square root of 1 plus 4t squared dt. Now, because the instructions say set up but do not evaluate, we don't have to worry about taking this any further. If you are interested in trying to take it a step or two further, be my guest. Be warned though, it's not a simple integral to evaluate. All right, the next thing we're going to talk about is we're going to talk about something that we call the arc length function. So this is kind of a strange idea, and it uses some kind of strange notation. But here's the idea. I've got myself a curve. And I want to start at some point over here that I'm going to call, let's say, A. And I would like to find the distance along the curve from that point A over to some kind of arbitrary point in time. Let's call that point T. Right? So here I'm actually using T as a stopping point. I don't want to use T as a parameter. I want to use T as just kind of a fixed value. I want to start at A, I want to stop at T. So in order for me to write down my curve using this notation, I'm going to represent the curve not as r of t like we normally do, but I'm going to write this as r of some other parameter. Let's use the letter u. So now I can say that this point here corresponds to where u equals a, and this point here corresponds to where u equals t. So if I wanted to find the arc length from that first point up to the second point where u equals t, this distance is not going to be a fixed distance. It's going to depend on where I stop. It's going to depend on that t value, right? If t is 1, I might stop here. If t is 2, I might stop here. If t is 3, I might stop here. If t is 4, I might stop here. So for different values of t, I should get different distances. So we're going to create this thing that we call the arc length function, which is s of t. And what s of t is going to be equal to is it's going to be equal to the integral from a up to t of the magnitude of r prime of u. And remember, now our independent variable is u. U is what's changing to give me the curve. So we're going to integrate with respect to u. So this is our arc length function. So give me a value of t, and I will tell you how far you have to travel from A to get to T along your curve. All right. Now, something that you can do with this is you can actually now work this until you get to some sort of function of T. And if you rearrange this equation, you can actually rewrite your curve as r not of u or not of t, but you can rewrite your curve as r of s, where s comes from your arc length function. It's not necessarily equal to your arc length function. It's actually what you get when you solve for t in terms of s. But what this does is actually something that's real fascinating. So in this situation, we call s the arc length parameter. And now if I sketch that same curve, let me even copy and paste it. So if I reparameterize this curve in terms of not u, but instead in terms of s, well, what happens is if I reparameterize this curve in terms of s, and let's say we go from maybe a to b instead of a to t, now what we get is we get that this length right here is equal to, so the arc length s, not necessarily the parameter s. Let me be a little more explicit there and let me say arc length is going to be equal to Well, just b minus a. So what we've done is we've now kind of thought about our curve or the bug or the insect or whatever you want to imagine walking around the page. We're going from thinking about its position as a function of time to now a function of the distance that it's traveled. So we've reparameterized this curve in terms of the arc length parameter. We've got something like this. This is actually incredibly useful because now we can directly compare distances traveled along curves. So I know that this idea is a little confusing. We're going to go through an example. I think it will still be a little confusing after the example, but that is a-okay. This is not going to be something that I want you to stress out a lot about. I just want you to have the idea in your head and know how the process goes in order to work through an example like this. So let's try example 57. It gives us the vector valued function r of t equals 4 cosine of t sine of t for values of t greater than 0, and it asks to find the arc length parameter for that curve, and then parameterize the curve in terms of the arc length parameter s. Okay, so let's go think through this. So the first thing we're going to do is we're going to find the arc length function. So our arc length function is this function s of t, which right above, we know that s of t is going to be the integral of the magnitude of r prime of u du from whatever starting point we want to start at. Well, in this case, we want to start at t equals 0 because we're looking for this for values of t greater than 0. So let's start at 0, and we'll go up to t. Right. So if we go through and we plug everything in, we'll be left with the integral from 0 to t. Our magnitude of r prime will be the square root of, well, we'll have a 4 times negative sine of t quantity squared, which will be a 16 sine squared of t, plus we'll have a 4 cosine of t quantity squared, which will be a 16 cosine squared of t. And I apologize, forgive me. We should be writing these in terms of the parameter u, not t. So I'm going to replace both of those t's that I wrote down with a u. And now we want to integrate with respect to u. All right, well, look at our integrand. We've got a square root of a sine squared plus a cosine squared with Pythagorean identity, but we have this factor of 16, so it's really a square root of 16, which is just going to be 4. So we're really integrating 4 from 0 to t. So if we go through, we evaluate the integral, we'll be left with a 4u from 0 to t, which is just equal to 4t. So we've got ourselves an arc length function, right? So what this means is this means that if we were to go look at our curve is just a circle that starts at the point 0, 1, and travels in a counterclockwise direction. So if I said, let's think about the point corresponding to t equals pi over 2. Well, when t is pi over 2, we'll be at the point 0, 4. But what our arc length function tells me is that if we start at t equals 0 and we go up to t equals pi over 4, that this little piece of arc length is going to be s of pi over 2 is going to be 4 times pi over 2, which is 2 pi. So the distance that we need to walk along our circle to get from the point 0, 1, or sorry, 4, 0 to the point 0, 4 would be a distance of 2 pi. Okay. So now what I have is I have this nice little relationship between s and t. So I know that s is equal to 4t, which means that I also know that t has to be equal to s over 4. So now what I could do is I can actually go back through and I could reparameterize my curve. I could now say that r as a function of s is going to be equal to 4 cosine of not t, but s over 4, comma 4 sine of not t, but s over 4 again. So I've replaced all the instances of t with s over 4. And now what I have is I have my curve parameterized in terms of this arc length parameter s. So now what this is saying is it's saying if you give me a distance traveled, I can tell you where on the curve you're going to be. So now if I wanted to know what r of something like 2 pi is, well, if I plug in 2 pi, that's going to have me at the point pi over 2, or where t equals pi over 2, or the point 0, 4 pi. I'm not going to write that out, so I will go ahead and delete that. So that's what reparameterizing a curve in terms of this arc length parameter does for us. It lets us now think about not a change in time and ask where we're at. It asks us, think about walking along the curve this distance. Now where am I at? Right. So we're going to use this idea to discuss something that we're going to call curvature. Now, curvature is kind of an odd topic to talk about because I think even if we've never heard the word curvature, or we've never used the word curvature, or we've never seen it, or we've never calculated it, we all have some sort of notion as to what curvature is. So here's kind of the curvature question, right? Which curve is curvier? So here I could sketch a nice little curve, maybe something like this. And I could sketch some other curve that maybe looks something like this. Right. And I think we'd look at this and we would say, well, obviously B is the more curvier of the two curves. Right? But if I followed that up with why? Well, there's a couple of good ways that you could rationalize it. You could say, oh, well, B has more turning points. B has more critical points. It has more extrema. You could say that B changes direction more often. You could say that B's derivative is higher. There's a lot of different things that you could say to try to justify why B is curvier. But this being a math class, we'd like to quantify this idea. We want to try our darndest to attach a number to why B is going to be curvier than A. And where the idea is going to come from is it's going to come from the idea of thinking about the change in direction as we move along the curve. So how we're going to do that is let's imagine we pick a point somewhere along our curve. So I'm going to imagine this point being at some r of t. And now what I want to imagine doing is I want to imagine drawing the tangent vector at that point. I'm going to ignore that lowercase t for just a little bit. That's something that we'll bring back up in class tomorrow. So I'm just going to draw the tangent vector at that point, right? And now what I want to imagine doing is I want to imagine walking some distance along my curve. So let's pretend I walk a relatively short distance, maybe however far that is. And now what I'm going to do is I'm going to draw the tangent vector at this point. So let me maybe label this T1 and T2. Right? So if I slide these together, right? Remember, vectors exist independent of their initial and terminal points. As long as they have the same magnitude and direction, they're the same vectors. So maybe what I'll do is I'll grab this vector T1, and I'll grab this vector T2. Oop, where'd the whole vector go? So what I have here is I have these two vectors. So this right here kind of measures how much my curve deflects as we walk along whatever that green distance is. We can call that some distance, I don't know, S. Seems reasonable to me. It's a little bit of arc length. So what these two vectors are doing is they're kind of painting a picture as to how much our curve is changing direction as we move over some distance S. Let's think about that maybe more as a little change in S. So maybe even I'll denote that as some delta S. Right? But let's look at the same picture the same idea if we go ahead and we look at the curve drawn under B. So I'm going to pick some point along my curve, let's say right about here. And I'm going to draw the tangent vector at that point on my curve. Might look something like that. So let's call that, we use T1, we use T2, let's call this T3. And now what I'm going to do is I'm going to walk along that curve the same distance that I walked along the other curve. So we'll call that a little change in arc length. We'll call that some delta S. So if I walk delta S along this curve, that seems about right. Now I'm going to be down here at this point, which means that if I sketch the tangent vector at this point, now my tangent vector is going to look something like this. So if I were to go ahead and I were to take these two tangent vectors, remember, I walked the same distance in this problem that I did in the previous problem, but now look at how much my tangent vectors deflect. So there's a much higher deflection amongst our tangent vectors walking along the second curve than there is along our first curve. So what this idea of curvature is going to be related to is it's going to be related to how much these vectors deflect. So kind of the angle between them as if I walk along the same distance between both curves. That's an idea that we're going to continue exploring a little bit tomorrow. We'll formalize it a little bit more tomorrow, and we'll come up with some cool formulas for it tomorrow. But with that, we're going to go ahead and leave that there for today. Thank you guys for hanging out. Hopefully you enjoy your break from me today, and I will see you tomorrow.